So this week we're going to take a look at 2.4, which is on graphing sine and cosine. Okay, if this was a full year class, what we'd probably do is we'd look at the other ones as well. Tangent, secant, cosecant, cotangent, all the other ones. But since we only have half year, we spend 1 week on graphing, and that's about enough time to get into sine and cosine. And what we're going to look at is different transformations. Okay, so we're going to look at 4 of them. And basically the transformations you can have are moving something up and down. That's 1. Left and right is 2. And then the other ones are stretching it. So you can stretch it up and down and stretch it left and right. So let's see. I'm going to show you guys just a couple examples. So I'm going to start with just kind of the basic graph. There's no transformations in this at all. It's just the graph of sine. All right. So let's do what it looks like. You can see it's not a line, it's not a parabola, it's a wave. Right? It's really the only graph that we have in math that looks like a wave. Well, sine and cosine, they both look like waves. This is an example of a transformation. Let's do sine of x plus 2. Okay, that plus 2, you took the graph that you had originally, and it just moved it up 2. Okay, that's a transformation. Another example, let's take the one we had in blue, and let's do sine 3x. Watch what happens here. What that does is it takes the graph in blue and imagine squishing it horizontally, kind of compressing it. Right? The waves get closer together. Right? So that's an example of another transformation. And we can play what that would sound like, right? Compared to what it would sound like if you didn't compress it. Right? But that's what the kind of graphs this week are going to look like. And let me show you the other graph we're going to look at, which is cosine. So I'll do sine again. And watch what cosine looks like compared to sine. Anyone describe to me how the one in red, which is cosine, compares to the one in blue, which is sine? Pete?
It looks to the left more, I guess.
Yeah, and that's exactly what it is. If you take the one in blue and you move it to the left a little bit, you get the one in red. So sine and cosine are very similar, except one is just a little bit to the left of the other. Now, this is a graph we're not going to look at this week. This is tangent. But just to show you what that one looks like, it's totally different. Okay, there is a pattern to it. Okay, all of these graphs, they repeat themselves over and over. Sine and cosine repeat themselves in a wave. Tangent repeats itself in these kind of like curves that go up. But again, not a graph that we're going to study. Okay, so we're going to focus on sine and cosine. Sine and cosine are what we call continuous functions. Continuous means I can put my pencil down, I can draw it, and I never have to lift my pencil the whole time I draw it. Tangent is not continuous. It's these separate sections that you have to lift your pencil, put it back down, and then draw the next one. Right. And because it's not continuous, that adds in a few things that are more complicated than sine and cosine. All right. So we stick with sine and cosine. So all the graphs that I showed you on the calculator so far, even the tangent one, which we're not studying, those are called periodic functions. And what makes something a periodic function is when it repeats itself over and over. So I'll come right back to that, but let me take and just do sine. Okay, so that pattern that you see, it keeps repeating. It's not like it actually ends. It only ends there because my screen ends there. But it does keep going. And if we want to see what it would look like if it kept going, all I have to do basically go like that. What I just traced out is one section, okay, of a sine wave. If you take that and make a copy of it, and then put it right there, there you go. That's what the next section would look like. And if you take it, copy it again, that's what the next section would look like. So the idea is the graph just keeps repeating itself once you've gone through one full, it's called a cycle, one full section of the graph. And from here to there is one full section of the graph. Everything else is just a copy and paste of what you see between those two green lines. So the way we can kind of describe it is we can say that all the y values repeat over a given set of x values. So in other words, after you've gone through a certain amount of the graph, you're going to start seeing the same values again. And when I say once you've gone through a certain amount, what is a certain amount? This is a certain amount between those green lines. And we can measure what that amount is. It's 1, 2, 3, 4 tick marks. How much is a tick mark? We'll talk about in a little bit. But it's 4 tick marks wide on my screen. Right. That's the set of x values that you have to go through, 4 tick marks. And then the y values start repeating. And if you looked at it, you notice that the graph, it only went up to a certain height, and it only went down to a certain height. Did anybody notice how high and low the graph went? Yep.
3.
Let's take a look and see.
1.
Yeah, so the highest it ever goes is 1, and the lowest it ever goes is -1. So the graph is always sandwiched between those two horizontal lines, 1 and -1, unless you transform it. Right? Like I showed you, you could take it, move it up, or you could move it down. Well, that's different. If you don't move it up and down, it's always going to be between those two lines, 1 and -1. Any question on that? So this information right here, this is just background information. It's nothing specific to actually doing a transformation yet. Right? I'll let you know when we get to that. But this is stuff that's just kind of describing how the functions we're going to work with all week. Just describing a little bit about them. Okay, so they are called periodic. And the length of that interval that I kept calling 4 tick marks, that is called the period of the function. Now, most of the time, the period is a certain number. And if you think about like on a unit circle, which we studied a couple weeks ago, think about how many degrees you have to go through to go all the way around the unit circle and get back where you started with. And then if you keep going, you're just repeating, going around the circle another revolution. Anybody remember how many degrees we got to go through? Yep, 360. So if we don't mess with the function at all, because we can squish it, right? We can squish it and make it more compressed. That changes the period, right? But if we don't do anything to it, the normal period is 360 degrees. That's the amount of distance you have to go through on the x-axis, like between those green lines, before the function repeats itself. We're going to be working in radians this week. So 360 degrees was correct, but we're going to just say 2 pi. So let me bring that graph back up that I had on the boards for a second. So from there to there is 2 pi. Or you could say 360 degrees. Once you've gone through 360 degrees of points, you're going to get the same graph repeated again. Right? So this section right here would represent another 360. And then here, another 360. So this is your x, this is your y. Your x-axis all week is going to represent an angle. Right? That's what the x-axis is. It's an angle. So if we were going to make a table, okay, when we start to graph this, we'll make a table like this. I'm not going to fill out the whole table right now. But the x value is going to be an angle. The y value is going to be, if you were doing sine, the sine of that angle. Or the cosine. Those are the two we're going to do. So we'll pick an angle, and then we'll plug that angle into the sine function, and that's how we get the y value. And we don't want to just pick random angles. We're going to pick certain ones that make this graph easy to do. Right? There are certain points that, if you find those, and I'm highlighting them in black, if you have those 5 points, that makes it pretty easy to draw the wave. Because you end up with the highest, the lowest, the beginning, the end, and the middle. That's about what you need to do a trig function. You need 5 points. And I'm going to write that down. Okay, but I have the picture on the screen, so I'm just showing you right now. All right. So this I've already said to you a few different ways. Again, once you graph one section, which is 360 degrees wide, after that, the graph just keeps repeating itself. Okay, another name for a period, which is the length of the interval before the graph repeats, is called the cycle of the graph. We don't use the word cycle as much. You might hear me say it now and then, but we generally don't use it as much. But cycles used a lot in other fields. Does anybody know what that stands for? Yep.
Hertz.
Hertz. It stands for hertz. And hertz is a measure of cycles per second. And does anybody know where you use hertz? Like maybe a field or an application where something is measured in hertz? Yep.
It's used a lot in radio frequencies.
Yep, so it's used in radio frequency all the time, right? If you turn the radio on and you turn it to, 107.3 megahertz, right? That's the frequency that the station is broadcasting at, so you can receive the signal. Right? It's a measure of cycles per second. That's a little bit different. That's radio waves, or what we call electromagnetic. I'm going to demonstrate some things to you in class, but I'm going to do it as sound. That's different than electromagnetic. Right? So we're going to do a few things as sound waves, not radio waves. But yeah, it's used in radio waves. You also see this if you do anything with electricity. Like all the electricity in North America, or well, actually maybe I'll just say the United States at least, it runs at 60 hertz. That's the frequency that when you plug something in, you're expecting to get from the wall. If you go to Europe, they run things on 50 hertz. So what that means is if you have a device that's only designed to work in the US on 60 hertz, and you go try to plug it in another country that doesn't use 60 hertz, it's not going to be a good day for whatever you plug in. It's probably going to ruin it. Now, if you look at like a cell phone charger or a lot of other modern types of things, like especially things that have the transformer on it, like your Chromebook or, again, most cell phone chargers, you'll see something like this, 50/60 hertz, meaning it's an adapter that's designed to be used in either one. So you can plug it in a European country, you can plug it in the United States, it'll work fine. There's nothing you need to do to adjust. It's fine. Something like your toaster, that could be a problem, right? If it's a toaster, because you think about a toaster, it just plugs in, right? There's no like transformer like your cell phone charger has. It's just like when you plug in a light. Don't know how well that would work in another country if it's not made for that. Probably wouldn't. All right. But again, so there are some areas that use hertz. We just we don't use cycles per second a lot. And if you look at, let me see if I can find. I have this program, which we're going to use to do some sound stuff in a little bit. Let's see. You can see it. It's kind of hard to see, but it does say hertz right here, and it says 1,000. So when you play a sound frequency, there's a pitch to it. How high pitch or low pitch does it sound? That's the frequency, which is measured in hertz. And again, if we have a little time at the end, I'll play some different sounds for you. All right, so I touched on that a little bit. Really, when you're graphing a trig function, you want to have 5 points. Some things you don't need 5 points. Like when you're drawing a line, you only need 2. And you get 2, that's good enough, you get a line. But when we're graphing a wave, it helps to know where the wave starts and stops, at least one section of it. The high point, the low point, and the middle. If you have those 5 points, you'll get a pretty good sketch. The other thing you want to notice here is there are no sharp points in these graphs. They're all curves. So you shouldn't have something like that. There is a name for that. That's called a sawtooth wave. It's a cheap way to approximate a sine wave. Sine waves are expensive. They're not easy to reproduce, especially if you have like a generator at your house. To have a generator that makes electricity that looks like that, nice smooth wave, that takes a lot of work. That's more expensive components in the generator. We can make an electrical wave that is a little bit more jagged, a lot cheaper. The downside to that is if you have any sensitive electronics and you have a really cheap generator, it might damage them over time. Probably not going to damage it, if you just use it here and there. But that's why if you look at some generators for houses, they have what they call an inverter built into the generator. That inverter is very expensive, but it puts out very, we'll call it nice looking electricity, right? Devices like it. Cheaper generators don't do that, right? So when we sketch everything, we want it to be a nice smooth curve. Okay, no jagged or sharp points. And I can play the difference if you want. We have a little time between a sound like this and a sound like that. You'll hear this top one. You can tell it sounds very different than the bottom one. So anytime that we graph a transformation of sine or cosine, we always have to have a starting point. Because if I said to you, I want you to take the graph and shift it up 2. Well, if you don't know where to start from, you're not going to be able to shift it up 2. we have to know where are we starting from. And we're going to have two different tables, one for sine and one for cosine. Now let me go back up and look at that graph for a second. There's 5 points. And just to keep the math easier to do in our head, even though we're going to work in radians this week, let's just do this part in degrees. That's 0. That's 360. What would be halfway between 0 and 360?
180.
So this would be 180. And what's halfway between 0 and 180? That would be this one. Yep,
90.
that's 90. And what do you think that last point down there would be? Yeah, 270. So look at the pattern. 0, 90, 180, 270, 360. When we graph sine or cosine, we're going to plot a point every 90 degrees. That's what we're doing. And if you plot a point every 90 degrees, you'll get the beginning, the end, the middle, the high, and the low. You'll get all of them. We're just going to plot these points in radians. So 0, pi over 2, pi, 3 pi over 2, 2 pi. Those are our x values. Again, we're picking those because they give us nicely spaced points. 5 points, all 90 degrees apart. Could we pick other points? Sure. But it doesn't really help you to get this point right here. I mean, if you've got this one and you've got that one, that's all you really need for that section. You don't need more points. You could do more, but you don't need them. So remember, these are angles. 0, pi over 2, pi, 3 pi over 2, 2 pi. Now, the y values are when you plug all of these numbers in for x. That's how you get the y value. So, if we take the sine of 0, you get 0. And there's your first y value. The next one is pi over 2. I'm going to plug pi over 2 in for x. And if you look at the graph, you already know what this value is. It's 1. So we start at 0, and we go to 1, and we go to 0, and we go down to -1, and then we go back to 0. Those are the y values. 0, 1, 0, -1, back to 0. This is a repeat of that. It's starting over again. 0, 1, 0, -1, 0, 1, 0, -1, 0, 1, 0, -1, 0. That's the pattern that we keep repeating. All right. Now, for cosine, it's pretty much the same idea. Okay, we're going to graph cosine, we want to graph 5 points. But if you remember what the graph looked like, or what I think Pete said it looked like it was a little bit to the left of the sine. It's still a wave, but what ends up happening is it usually looks something like this. So if I had a wave that just kept going, I'll erase that in a second. What we're sketching when we do cosine is that section of the wave. So it looks kind of like a V shape, but it's really just the trough of the wave. Okay. Where when we do sine, it starts at the origin. So the graph looks more like a wave. Okay. So we start at 0 and we're at 1. That's my y value for cosine. Then I go down to 0, -1, 0, and then I always finish the cycle exactly where I started, because now I'm beginning the next section. Okay, and those are my points for cosine. So anything we do all week, these two tables, we got to make sure you have those right. If you have anything copied wrong in those tables, it will mess up every problem that you do on the test. Okay. Any questions on those two tables? Yes?
So for the test, can we have a reference sheet for the tables?
Yes. And the hardest thing about this week, really, it's going to be arithmetic. You're going to have to work, when we do transformations, these numbers are going to change. When the ones in the right column change, that's not bad, because all you're going to have to do is arithmetic with ones, zeros, and -1s. That's easy. When the numbers in the x column change, you're going to have to do arithmetic with fractions that have pi, which means sometimes we need to find common denominators, things like that. Okay. The other thing to mention, you might notice, like, this is pi, right? Pi is 3.14. We're never going to write 3.14. Okay? None of these numbers are ever going to be rounded to decimals. Okay? So if you have a fraction and it has pi in it, leave it. Don't round it off. All right. So once we know where our graph is going to start from, we can determine where it's going to move to. So when I say determine where the 5 original points are going to move to, start with the table and then figure out how the graph is being transformed. And that's what we're going to learn the rest of the week. Is it moving up? Is it moving down? Is it stretching up and down? Is it stretching left and right? What's happening to the graph? That's what you have to figure out in this step. Now, one thing that is going to make it a little bit easier for you is every problem that we do is only going to have one thing happening in it. You're never going to have a problem that I give you where the graph is going to move up and left at the same time. That's two things. Okay. Every problem will only have one thing happening at a time. So, let's say I give you a problem where the graph moves left. Well, if you move left, that affects values on the x-axis. The x-axis is what goes left and right. So you had a point like this, and then it moved left to here. That point still has the same y value. It still has the same height. All it did was move left, so maybe the x value was at 0, now it's at -4. But it moved left. One column, when we do a transformation, will always stay the same. The other column will change. But you'll never have both columns changing at the same time. Only way both columns could change at the same time is if I gave you a transformation like shift it up 5 units and then shift it, right 6 units. Well, now you're doing two things at once. We're never going to do two things at once. Okay, and just in case there's any confusion, you're like, wait, what column is he talking about that's going to stay the same and what column is going to change? I'm talking about these columns right here. One of these columns will change, the other one will stay the same. Which one? Depends on the problem. I don't know. Depends on what we're doing. All right. So now I'm going to explain the one transformation we're going to look at today, which is called a phase shift. So a phase shift is really just a fancy word or term that describes when a graph is moved left or right. That's a phase shift. So what you're going to have to be able to do on the test is when I give you a formula like that, we're not doing it yet, but we'll in a little bit, you have to be able to recognize that, wait, oh, that's the equation for a phase shift. There's something in that equation that tells you it's a phase shift. We're going to talk about what you look for right now. That's a phase shift. That's a phase shift. That's a phase shift. So you might notice the pattern here. It's not just sine x. This would be, that's what we call the original. There's no transformation. But I've subtracted something inside the parentheses. I've added something inside the parentheses. I've subtracted something inside the parentheses. That's what you look for. So anytime that you add or subtract inside the parentheses, that is the equation of a phase shift. And it could be sine or it could be cosine. As I went through some of those examples I just showed you, some said sine, some said cosine. That part doesn't matter. This part just controls which original table you start with. And I gave you two, the sine table or the cosine table. And if you start with the wrong one, it's no good. Now, technically, you can add or you can subtract any number you want. It's just moving it left and right. Remember, left and right is the x-axis. X-axis is in radians. You could shift it right by 1.6 radians. You could shift it left by 2.447. You could. But we usually shift it by certain amounts that are standard. In degrees, those amounts would be like a 90-degree shift, a 180-degree shift, or a 360-degree shift, 45-degree shift. Those are common. We don't usually shift something by like 1.456 radians. You could, but it's kind of a weird amount to do. Right? So you'll see a lot of standard numbers for C that we use. So obviously when you're shifting horizontally, there are two directions you can go, left and right. And you might have noticed some of these problems have a minus, some of them have a plus. Well, the difference is some of them are going to go left, some of them are going to go right. So these two rules tell you whether or not the graph is going to move to the left or to the right. And it's not what you would expect. You might think, like if you think of a number line, negatives are on the left, positives are on the right. That's true. But when we do a phase shift, if you do x minus something, a minus causes the graph to go to the right. How much to the right? Well, it depends on what the value is. If it was x minus pi, then it would move to the right pi. If it was x minus 2 pi, it would move to the right 2 pi. Depends on how much that value is. So a minus is going to cause the graph to move to the right. What do you think is going to happen for a plus? Yep, Angelina? It's going to move to the left. And again, it might not be what you would think. You might think, oh wait, positive numbers are on the number line as you head to the right, but it just doesn't work that way. It's the opposite of what you would expect. So minus will shift right, plus will shift left. All right. So the last thing we'll do is I'll just go through a couple steps for how to actually do the graph. Talk about which column is going to stay the same and which column is going to change because you're only moving left or right. So the up and down isn't affected. We just have to figure out which axis is the up and down. And then we'll know that axis isn't changing. Okay. So we're moving left and right. Which axis is the axis that goes left and right? Yeah, the x. So the x values are going to change when you do a phase shift. Unfortunately, because the x values are changing, that means you're going to have to do arithmetic with numbers in the x column. That's the harder column to work with. So the x column is going to change. The y column is going to stay the same. So when we do a phase shift, the first thing you can do right away is look at the problem, figure out if the problem is a sine or a cosine problem. This one will be a sine. Go to the original table for sine and copy down the y values in that table because they're not changing. And just by copying the y values from the right table, you would automatically get 5 points. Because what I'll do is I grade each one of these numbers as a point. So if you copy the y values down correctly, 1, 2, 3, 4, 5 points. Copying those down. Now, to get full credit for the table, you've got to get the x values right. So, remember what we said. Minus is going to move it to the right. Plus is going to move it to the left. So it's the opposite of what you would think on like a number line. So first thing we want to do when we have a phase shift is look at the problem and say, okay, we have a minus pi over 2. We know that minus is going to move things to the right. What happens to numbers as you go to the right on a number line? Yep. They increase, they get bigger. The only way to make a number increase is to add to it. So, you look at your problem to find the new x's, look at what's been added or subtracted in your problem, and then you do the opposite. Right? We have a minus in the first problem. We know minus is going to move everything to the right. If things move to the right, they're getting bigger. The only way you can make things bigger is really to add. So that's why you have to do the opposite of what you see in the parentheses. And on your reference sheet, it's going to be important to keep track of, wait, is this, he taught me 4 transformations this week. Is this one of the transformations where I do the opposite? Phase shift is. It's one where you do the opposite. We're going to learn other transformations tomorrow and Wednesday where you don't do the opposite. Okay, so you got to, somehow you got to keep that straight. All right, everybody have step 2? So the last thing we'll do is look at 3 different examples and do some sketches.
Okay, you should go back up to number 1.
Yep, so number 1 is just that the y values stay the same. For a phase shift. When we learn other transformations, it might be the x values that stay the same. All right, So let's look at this one. All right, so they want us to graph y equals sine of x minus pi over 2. Now, even though it says graph, I'll tell you right now on the test, the graph is going to be worth very little credit. What's going to be worth the most credit is the table that you make. The table is going to be worth 10 points in every problem because there's 10 numbers in the table and you get credit for each number that is correct. So if you get some right and some wrong, you get partial credit. All right, so what I've done here is I've copied down the original table for sine. You already have that in your notes, a couple slides back. I just copied it over. Okay, so we know this is a phase shift. We're adding or subtracting inside the parentheses. Ben, what column stays the same for a phase shift?
I don't know.
Yep.
Yes.
The y's stay the same. Okay, so when we're doing a phase shift, the y's stay the same. Copy the y values from the original table into our new table. That's the original. Here's my new table. When I sketch this graph, it's going to have the same y values as the other graph. 0, 1, 0, -1, 0. Now, does it make a difference if I copy the y values from the sine table versus the cosine table? Yes. Those are different y values. Just look at them. They're not in the same order. Okay. All right. Now, have I added or subtracted in this problem? Pete?
Subtracted.
Subtracted. And can you tell me what I've subtracted?
Pi over 2.
I subtracted pi over 2. So I'm going to do the opposite of that to each x value. So Pete, what's the opposite of subtracting pi over 2?
Add it.
Add it. Good. So we're going to take all these original x values. I'm going to just copy them right here. Pi over 2. Pi, I'm leaving a little space to do some work. 3 pi over 2. 2 pi. And I'm going to take every one of those x values and I'm going to shift them all to the right. How much to the right? Pi over 2. So we're going to go plus pi over 2 on each one. And what that's going to do is shift every value to the right, pi over 2. And we have to figure out what that is. So inside that table is what I would be grading. This is the work to figure it out, and then we have to put the answer in the table. All right, so let's start with 0 plus pi over 2. How much is that? Yep, Angeline? Pi over 2. Now, we haven't run into this yet, but what happens when you have fractions and you want to add them together? You got to make sure, what? Yep.
The denominator's the same.
Yep, you got to make sure the denominator is the same. That doesn't look like a problem here. So remember, when you want to add fractions, you keep the denominator the same, and you add what's in the numerator. So what's pi over 2 plus pi over 2? Yep.
2 pi over 2.
So I'll write that right here, off to the side a little bit. It is 2 pi over 2, which reduces to just pi. The 2 pi over 2, though, it's going to be handy because you're going to see a pattern in a minute. Reducing it is preferred, okay? But I want to leave it not reduced right there so you can see a pattern with these values. All right. How about Aiden? The next one. What's my denominator for pi? Because I don't have one.
It would just be 1.
Would just be 1. Do I have a common denominator there?
No, so you would multiply it by 2.
Yep, we're going to multiply the top and the bottom by 2. Now we have 2 pi over 2 plus 1 pi over 2. Pete?
3 pi over 2.
3 pi over 2. Notice you can't reduce that one. Okay, next one already has a denominator of 2, so we're ready to add there. Ava, what's 3 pi over 2 plus 1 pi over 2?
I'm not sure.
Well, just pretend that the pi isn't even there. What's 3 over 2 plus 1 over 2? So it'd be 4 over, and you keep the denominator the same.
Oh,
2. Right? So 3 pi over 2 plus 1 pi over 2 is going to be not 4 over 2, but 4 pi over 2. All right. So if I write 4 pi over 2, what does 4 pi over 2 reduce to? Yes?
2 pi.
2 pi. Good. 2 pi. And the last one, kind of like the one I asked Aiden about earlier, there's no denominator there. So let's make it a 1. And Colby, what could I do to get a common denominator there?
Multiply by 2.
2 in the top, 2 in the bottom. And what's 2 pi over 2 plus 1 pi over 2?
5 pi over 2.
5 pi over 2. And there's our table. Okay, we're done. Now, read down the x column, but read the values that aren't reduced. 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2. Anybody have a guess what the next one would be if we were going to keep going? We're not. Well, what would it be? Yep.
6.
6 pi over 2, 7 pi over 2, 8 pi over 2, 9 pi over 2. So if you see a pattern in your x values, then you probably did it right. If you don't see a pattern, then something's probably wrong. Notice though, the pattern's only easy to see before you reduce it. Once you reduce it, you don't have a denominator of 2 anymore. So to look for a pattern, you have to have the same number in the bottom of each one. Okay. And this would be worth 10 points on the test. 1 point for the x's, so that's 5, and then 1 point for each y. Okay. Any question on that? Now, does anybody remember what we said earlier? We picked values that were all spaced apart by how many degrees? Originally, yeah? They were all 90 apart. So think about if you take a bunch of points that are all the same distance apart. Right, here's another copy of them right here. And you take all those points and you shift them to the right. Like that. Are they still all the same distance apart? What do you think? Yeah. Yeah, they're all the same distance apart because you moved every point exactly the same amount. So the points are still equally spaced. So when we put these on a graph, we're going to make sure that we make sure they're all equally spaced. All right, so we're not using 0. Okay, if it helps to think of it in degrees, kind of off to the side, you could do that. This top one is 90. That's 180. That's 270. That's 360. And this bottom one is 90 times 5, 450. Okay, so they're still 90 apart. We're just starting at 90. We're not starting at 0. So that's 0. That's 90. 180. 270. 360. And 450. It does get a little squished sometimes, so you kind of have to write your numbers small, but that's okay. All right. So that's one thing you always have to make sure you do. Put your labels on the x-axis, and now graph your points. Pi over 2, 0. Next one. Pi 1. Pi 1. Okay. 3 pi over 2, 0. 2 pi, negative 1. 5 pi over 2, 0. And there is your graph. So, I'll just color code it. This is the new graph. The original would have looked like, let's go like this, like red, right about like that. So the original would have been in the one in red, bless you, and the black one has been pushed to the right a little bit. Okay, any question on that? So what I'll have you do in the homework is I'll set up 2 graphs, and I'll have you put the red one on the left, and then I'll have you put the black one on the other one. I guess you could put both on the same. That's kind of handy to compare them, but I separate. All right, last one. So this is a cosine. Can anybody tell me, besides it's the only thing I taught you all week, why this is a phase shift? What makes this a phase shift? Angela?
It's plus inside the parentheses.
Yep, it's plus inside the parentheses. Plus or minus inside the parentheses is a phase shift. Plus or minus outside the parentheses we'll talk about tomorrow. Okay, and is this a sine or a cosine? That's an easy question. Yep. It's cosine. It's a cosine. So, xy. Angelina told us it's a phase shift. So we automatically should know one of these columns is not going to change. Which column does not change for a phase shift? Yeah. Good. The y's. So let's go to our cosine. Let's copy down the y's. And that's the first part. So cosine y values, 1, 0, negative 1, 0, 1. Copy those down. All right. 1, 0, negative 1, 0, 1. Now, we can also copy down the original x's, because we're going to do a little arithmetic with them. I'm not going to put them in the box, because they're not the answer, but I'm going to do something to all of them. Can somebody remind me, what are my original x values? And these are the same for sine and cosine. Jess?
0, pi over 2, I, 3 pi over 2, 2 pi.
But now we're going to modify all those. We're going to shift them all by doing something. Can anybody tell me, what am I going to do to every one of those values? Yep?
Subtract pi.
Good. We're going to subtract pi, because we know when we have a plus, plus is supposed to move things to the left. The only way you can move things left is if you make them smaller. So minus pi. And some of these are quick because we already have common denominators. The top one is negative pi. The third one is 0. And the fifth one is 1 pi. We have to figure out the two that don't have common denominators. All right, so Autumn, what's my denominator if we don't have it?
1.
1. And we're going to have to fix it, so we do have a common denominator. Jacob, what's my common denominator between 1 and 2?
2.
2. So let's do a times 2 and a times 2. Right. Dom, what's 1 pi over 2 minus 2 pi over 2?
Sorry, doesn't matter where we sit.
No.
Very cool.
Negative 1 pi over 2.
Very good. 1 pi over 2, take away 2 pi over 2 is negative 1 pi over 2. Same deal here, common denominator. Times 2 in the top, times 2 in the bottom. Lacey, what's 3 pi over 2? Take away 2 pi over 2. So what's my denominator going to be?
Oh, pi over 2.
So yeah, that's going to always stay the same, and pi is in the top. And if you look and you're like, well, where's the pattern here? Well, we don't have a denominator of 2 on everything, but if you did, that'd be negative 2 pi over 2, negative 1 pi over 2, 0 pi over 2, 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2. Okay. Any question on that table? So we've got x values that were all evenly spaced to start with. We shifted them all to the left. They're still all evenly spaced. So let's set up our graph here. So we need negative pi over 2. You don't have to label the axis as 0. The axis is always 0, but you can. Pi over 2, and pi. And if ever I get confused with the labels, I change them to degrees and see if they make sense. Negative 180, negative 90, 0, 90, 180. Yeah. Each one basically represents 90 degrees, and we're starting at negative 180. So that's perfect. And now just graph your points. 1, 0, negative 1, 0, 1. 1, 0, negative 1, 0, 1. Now, that's not a V. Remember, all our graphs look like that. It's that section. It's a wave, so don't make it pointed. Try to make it as curved as you can. Basically, make it look like what's in that box. Close enough. Not perfect, but good enough. And that's all you ever have to draw. You don't have to keep drawing. If I wanted you to draw more, all you'd have to do is copy and paste that again, and you could get the same sketch. Okay? Any questions on that one? Okay, last one. Okay, so we're going back to sine. And this time it's a minus. So let's make our table. And then when we set up the graph, we have to be a little careful. And I think you'll understand why once we get the table. All right. How about Mateo? What column stays the same?
Y.
The y's. Does anybody remember what my y values are for sine? Yeah.
0, 1, 0, negative 1, 0.
Perfect. You got 5 points just for getting those right. Now let's put down the original x's. Don't put them inside the box. So let's write those down. Olivia, what are my original x's for sine?
0, pi over 2, 5, 3 pi over 2, 2 pi.
Good. All right. Now we're going to modify all of those. Well, Cassidy, what am I going to do to all these x values?
Minus pi over 4.
Well, minus pi over 4 is what's in the original problem. Notice, like on this one, when we had plus pi, we did minus pi.
Oh, the opposite, so Add pi over 4.
Yeah, we're going to add pi over 4. So you'll notice we don't have any common denominators. We're going to have to find common denominators for all of them. But it's going to be the same common denominator every time. What's going to be my common denominator for all of these? Yep.
4 or 8?
4.
Yeah, I'll say 4.
So I guess I should be more specific. What is the least common denominator?
4.
Yeah, 4. So the first one, that one's pretty easy. 0 plus pi over 4 just gives you pi over 4. All right. So Pete said common denominator is going to be 4. Autumn, what would I multiply top and bottom by?
2.
2 and 2. And then what's 2 pi over 4 plus 1 pi over 4? Ben. Done?
3 pi over 4.
2 pi over 4 plus 1 pi over 4. 2 plus 1, 3. Right, let's look at the next one. Pi. How about Colby? What's my denominator on this one?
1. Well, you're changing it.
What is it right now?
1.
1. And what am I going to change it to?
4.
Perfect. Times 4 times 4. And Lacey, what's 4 pi over 4 plus 1 pi over 4?
5 pi over 4.
5 pi over 4. Now we might be at a point, can anybody see the pattern? 1 pi over 4, 3 pi over 4, 5 pi over 4. If we see the pattern, we can just write it. Yeah?
7 pi over 4.
7 pi over 4. And how about the last one?
9 pi over
Go ahead. Go on. Yeah, anyone.
9 pi over 4.
Yeah, 9 pi over 4. So the pattern here is odd numbers in the numerator. 1, 3, 5, 7, 9. Okay. Question on the table. All right, let's look at the graph. And let's focus on the numbers in the numerator without pi over 4 just for a second. 1, 3, 5, 7, 9. Say we were making a number line. And you wanted to put the numbers 1, 3, 5, 7, 9 on it. I could put 0 there, that's fine. Where would 1 go? Yeah, Olivia?
Right next to 0.
Right next to 0. Remember, these are the numbers we're going to put on it. Now, where would 3 go? Yeah?
2 takes over.
Why did you skip 1?
Because you have enough space to do it as if there's... You have enough space to do it as if there's actually a full number line.
Right, here's another question. I'll ask it this way. Why not put it right there?
Because although you're not using it, that would be 2.
That's 2. Yeah, you can't use that as 2. So 3 has to go there. Whatever gap you set between the first 2 numbers, you have to keep that gap the same all the way through. Your gap here is 1. So the next gap is a 1. And then the next gap is a 1. And the next gap is a 1. So now where would 5 go? Jess?
2 over from there.
It would have to go 2 over. And the 7 and the 9. We're going to label this number line exactly the same way when you have a pi over 4. You end up having to skip because the same reason you have to skip when you do 1, 3, 5, 7, 9. So if this is 0 and this is 1 pi over 4, then this next one is 2 pi over 4. So we want 3 pi over 4. if you want to label 2 pi over 4, you can label it. We're not using it. Just like here, if I want to label these, I can put in the labels I'm not using. That's fine. Just putting more labels than you need. Okay. But we've got 1 pi over 4, 2 pi over 4, which I'm not going to label because we don't really need it. 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4, 8 pi over 4. I'm really on the edge. And you got 9 pi over 4. I think that's as high as I need. All right, 0, 1, 0, negative 1, 0. 0, 1, 0, negative 1, and back up to 0. Well, not perfect, but it's pretty good. All right, so keep that idea in mind that sometimes you need to skip. That usually happens with the pi over 4. But that's when the skipping thing seems to come up. And if it's confusing, just think of it for a minute without the pi over 4s. How would you do 1, 3, 5, 7, 9? You're going to do those the exact same way. All right, any questions on that? All right, so the homework tonight is a worksheet. Okay, again, I showed you the worksheet at the beginning of class. It's in Schoology. And just to show it again in the video, we're going to go to 2.4, part 1. It says phase shift. Click on phase shift, and then there's a PDF file right there with the homework. Okay.